Welcome to the fourth lesson in our series of motion in one dimension. In the previous lesson, we looked at equations of vertical motion. At the end of this lesson, you should be able to define and specify a frame of reference and calculate more complicated vertical projectile motion. In the previous lessons, we made a very important assumption. Join me, and I'll show you what I mean. I'm walking across the car park to the children's play area. The tar under my feet looks as if it's absolutely still, without any motion. The same is true of parked cars. As I go past this car, you can see that it's motionless. Here, the children are jumping on the trampoline. It appears that the only things moving are the children and the trampoline's springy surface. The only problem is we didn't consider the motion of the earth. Up to now, we've assumed that the trampoline and the children on it are not moving on the earth. This isn't entirely true. As you know, the earth is continuously rotating on its axis while simultaneously moving in orbit around the sun. Right at this second, the earth is moving slightly while the children are jumping and while I'm standing still watching them. In our previous calculations, we assumed that the earth was not moving and therefore we made the earth our frame of reference. A frame of reference is simply the point that we consider to be the 0 point. So until today, we have considered the motion of objects independent of the earth's motion. When the children are simply sitting on the trampoline, it would appear to us on the earth that they are not moving. However, if we were able to look at the children on the trampoline from the moon, using a very powerful telescope, we would see a different situation. To the observer on the moon, the children are moving slowly with the rotation of the Earth. In this case, the point of reference is the moon. Let's consider another situation. A wonderful, peaceful way to get an amazing view of the city or countryside is to take a trip in a hot air balloon. A basket is attached to a huge balloon. Then the balloon is filled with hot air. Hot air is less dense than the cooler air surrounding the balloon. This causes the balloon and the basket to rise. Sandbags are attached to the balloon to help stabilize the balloon during its flight. If one of the sandbags comes loose, it falls to the ground while the balloon continues to move up. We can consider this situation from 2 points of reference. Firstly, using the balloon as a point of reference. Relative to the balloon, the sandbag's initial velocity is 0, and it will move downwards away from the balloon. Secondly, using the Earth as a reference point. Relative to the Earth, the sandbag's initial velocity is not 0. It is the same velocity at which the balloon is moving. So the sandbag will first move up, slow down, and come to a stop before falling to Earth. If we consider the initial velocity of the balloon relative to the ground, the sandbag's initial velocity is equal to that of the balloon's velocity because it is attached to the balloon. We can prove this in a laboratory. To demonstrate how a sandbag moves when it falls off an upwardly moving hot air balloon, I'd set up a camera and take photographs as this ball moves. I'd hold the ball in my hand so that I can release it while moving upwards. I'd set the camera to take photographs every second once the ball has been released. I see Nombulelo is back with us, so before we check the results, let's find out if she's been following us.
Hi Sivu, it's been interesting so far. I'm looking forward to figuring out how to use all this data in equations and graphs.
We'll soon get to that, Nombulelo. Examining the image obtained during the experiment, we clearly see that the ball moved up first before falling down to the earth. Let's put all this data into a table to help us analyze the motion. As always, we are going to choose a direction as positive. Since the ball moved up originally, we'll make up the positive direction. During the experiment, the velocity of the ball was always measured and recorded in this table. Using the information in the table, can you calculate the acceleration of the ball? There are many ways to calculate the ball's acceleration. Let's calculate the ball's acceleration after half a second. Nombulelo, How do you choose a formula to use?
Well, we know the initial velocity and the final velocity, as well as time. This should help. So it must be Vf equals Vi plus A delta t.
Yes, we use the equation final velocity is equal to initial velocity plus acceleration times change in time. So 4,9 is equal to 9,8 plus acceleration times 0,5. Then we subtract 9,8 from both sides. Therefore, 0,5 A is equal to negative 4,9. By solving for acceleration, we see that A is equal to negative 9,8 meters per second squared. This value of negative 9,8 isn't a surprise, is it? The ball accelerated due to gravity acting downwards, which was the direction we chose as the negative direction. We could repeat this equation for every part of the motion and we will get the same results every time. So our table now looks like this. I trust you understand. The ball wasn't moving relative to my hand, but it was moving upwards relative to the earth. So its motion was the same as it would be if projected vertically. Now let's plot the graph of position versus time for the motion of the ball. As with all the other graphs we have drawn so far, time is on the horizontal axis and displacement is on the vertical axis. Remember though, it will be necessary to extend the vertical axis to include the negative values recorded. We plot the points on the graph. Now that we've plotted the points, we'll join the points together freehand. This graph must be a curve due to the fact that the ball is accelerating.
Oh wow, look at that. The graph has the same shape as the photo of the motion. Amazing.
Yes, take a look at this. Okay, now we'll draw the velocity versus time graph of the motion. What shape do you expect the graph to have?
I'm sure it must be straight. I remember that from the last lesson.
Of course, it will be a straight line. Time is on the horizontal axis and velocity is on the vertical axis. Because the ball drops below its starting position, there will be negative velocities, so the velocity axis is extended to include negative values. Once the points have been plotted, a straight line can be plotted. There is only one more graph to be drawn, the graph of acceleration versus time. This is the simplest graph as the acceleration is constant and has a value of negative 9,8 meters per second squared. All three of these graphs have the shapes that we expected. Here's another example. The graph shows the motion of a tennis ball that was thrown vertically upwards from an open window, same distance from the ground. It takes the ball 0,2 seconds to reach its highest point before falling back to the ground. Study the graph carefully. Question 1. Calculate how high the window is above the ground. To answer this question, we'll return to the graph. At the beginning of this motion, which is where time is 0, we can see from the graph that the tennis ball was 4 meters above the ground. Question 2. Calculate the time it takes the ball to reach the maximum height.
Could we see the graph again?
Yes, it would help us to answer this question. The tennis ball will have reached its maximum height at the point in the graph just before it starts to change direction. Here, this maximum point has been highlighted. From this position, we can read off the time it takes to reach this point. So the time taken is 0,2 seconds. Question 3. Calculate the initial velocity of the ball. Remember that we could calculate the velocity of an object from this graph by drawing a tangent and calculating the gradient of the tangent. But this is tricky on a curve, so we use another method. We take values from the graph as well as some implied information. How do you suggest we start, Nombulelo?
With a list of information we already know.
Quite right. Let's list the information we know. The final velocity is 0 because the ball is at the top of its motion. Initial velocity is what we are looking for. The acceleration is the acceleration due to gravity, so it has the value 9.8 meters per second squared. The upward direction was taken as positive, so acceleration is negative as it acts downwards. The time taken is 0.2 seconds, calculated in the previous question. This information gives us clues as to which equation we should use, which is final velocity equals initial velocity plus acceleration times change in time. 0 is equal to initial velocity plus negative 9.8 times 0.2. Therefore, 0 is equal to initial velocity minus 1.96. Now we solve for initial velocity. We say that initial velocity is equal to 1.96 meters per second up.
I'm really getting the hang of this now.
Great. Ready for another question? Question 4. Calculate the maximum height that the ball reaches. This value cannot simply be read off the graph because the graph wasn't drawn to scale. So we will need to use an equation of motion again. Let's go back to the information we know. We can now include the value of the initial velocity because we have just calculated it. From this list, can you see which equation we can use? There are 2 possible equations we could use to solve this problem. Which one do you think we can use, Nombulelo?
There's one in our formula sheet that uses final velocity squared to get change in displacement. Or maybe we should use this change in time squared.
They are both correct. Either we could use final velocity squared is equal to initial velocity squared plus 2 times acceleration times change in displacement. Or change in displacement is equal to initial velocity times change in time plus half times acceleration times change in time squared. We're going to use the second equation because displacement is already the subject of the formula. So the maths will be a little easier. Think you can do this? First, we substitute in what we know. The change in displacement is equal to 1.96 times 0.2 plus half times negative 9.8 times 0.2 squared. Therefore, change in displacement is equal to 0.392 minus 0.196, which means that the change in displacement is 0.196. I wonder if you have noticed something. Is this the final answer? Calculate the maximum height that the ball reaches. What we calculated is simply the distance that the ball moved above the window. So we have to complete the answer. The maximum height is actually 4 plus 0.196. This equals 4.196 meters above the ground. For calculations, we normally round off to 2 decimal points, so this will be 4.20 meters. Finally, question 5. Calculate the final velocity of the ball when it reaches the ground. There are several ways to calculate this final velocity. We're going to look at the one method in which we consider the entire motion from start to finish. A list of information looks like this. The final velocity is what we are looking for. The initial velocity is 1.96, calculated earlier. Acceleration is negative 9.8 meters per second squared. The total displacement of the ball is negative 4 meters. This is because the ball ends 4 meters below the window and down is the negative direction. The equation to be used is final velocity squared equals initial velocity squared plus 2 times acceleration times change in displacement. So final velocity squared is equal to 1,96 squared plus 2 times negative 9,8 times negative 4. Therefore, after doing the maths, final velocity squared is equal to 82,2416. The final velocity is then square rooted and is equal to 9,07 meters per second down. Are you ready for more? Well then, here's this lesson's task. Consider this information. At a height of 20 meters above the ground, this camera will fall while the hot air balloon moves up at a velocity of 4 meters per second. Here's the question. A tourist takes a trip in a hot air balloon. The hot air balloon is ascending or moving up at a velocity of 4 meters per second. He accidentally drops his camera over the side of the balloon's basket at a height of 20 meters. Calculate the velocity at which the camera hits the ground.